So now we'll move ahead with the keynote talk for today. We have Dr. V. Ashok from VSSC ISRO. So I hope he has joined by now.
We are delighted to have Dr. Ashok, Associate Director, VSSC. Thanks to contribution of people like him, ISRO has been making, amazing things. And in fact, whenever I give a talk on either FOSSEE or spoken tutorial, I always start by saying that how ISRO's missions are a lot cheaper than somebody else, whether it is movie gravity and so on and so forth. All these have been achieved by silent contributors like Dr. Ashok. We are delighted to have Dr. Ashok to address this audience, and there are many students who are joining also, research scholars, and we look forward to benefit by your wisdom, Dr. Ashok. Thank you.
So thank you, and so I will in my half an hour talk, I will briefly cover on the CFD applications in space missions. And I am extremely glad that IIT Bombay is looking on the open source software platform. In fact, in Vikram Sarabhai Space Center, we do use OpenFOAM. We use DSLC foam, which is the direct simulation Monte Carlo foam for the very rarefied flows. On the other open source software, we use SU2 for our compressible viscous flows. But then we also have our own codes, which I will cover in my talk. So I'll briefly cover on the various applications so that you will get a flavor of what are the types of problems which we do. And as you know, the space system technology is multidisciplinary. Of course, it has mission design, propulsion, aerodynamics, thermal design, etc. And so the CFD comes mainly in propulsion, aerodynamics, and thermal designs. Of course, and this inputs goes to structures, navigation guidance, etc. I myself have been the aerodynamics background, and almost 35 years I spent in VSSC, and I had worked on the computational CFD core development and also on its applications. So now, if you have to sum up the various challenging problems in the launch vehicle missions, this is one slide that will tell you which are the very interesting problems which are there. Right from the liftoff to the injection of satellite, we have various problems which are there. And if you see at liftoff itself, we have the jet interactions with tower interactions and wind dispersions, and there are a lot of issues there also. And then moving on to the atmospheric phase of flight, if you see there is where you have the propulsion structure control aero interactions, and then we have the shock oscillations, unsteady loads, base heating. These are all in the atmospheric region of flight. And then subsequently you have the closed loop guidance, etc., and injection into the orbit. So we will mostly focus on some of the interesting problems during the aerodynamic phase of the flight. And if you see, if you want to sum up the problems which are there, on the left hand side you have the aerodynamic problems, and on the right hand side you have the aerothermal problems. You can see that there's a compartment venting and the shock oscillations which cause the buffet. That means we have to quantify the unsteady forces. Of course, this particular aspect is still a very challenge for CFD because still we rely on experiments. And then there is also the aerodynamic noise which is coming on the strap-on shock interactions. Then there are some jettisoning rockets which will be used for separating the strap-ons and the lift-off aerodynamics. These are some of the important things which are and multi-jet interaction and aero loads on nozzles. So these are some of the things. But we have also special problems like the re-entry aerothermodynamics, flow and combustion studies in air-breathing engines, dynamic stability of re-entry capsule. This is one of the very interesting problems. That is, we have to calculate what is the dynamic stability of this, what is the aerodynamic damping that is coming when there is oscillations of the screw module during the re-entry phase. And we also have the two-phase flow with with combustion. That is also a very interesting problem. And as you know, in CFD, we solve this Navier-Stokes equation, and I don't have to tell this audience about this equation. This is very, very familiar, and this is on a structured grid on a re-entry capsule. And as you know, these are the very steps involved in you generate a mesh, and then you calculate the cell areas, volumes, calculate the invasive fluxes after reconstruction, and then you have the viscous fluxes. You march in implicitly or explicitly satisfying the stability criterion and update till you get convergence. So this is a very standard finite topology. Now let me tell very briefly about some of our solvers which we have. One is the parallel aerodynamic simulator, which is on a Cartesian mesh, so which has a very automated Cartesian mesh, and which has a K epsilon turbulence modeling, invisible fluxes using an approximate Riemann solver. We use the primitive variable Riemann solver, and viscous fluxes by central differencing. We have a second order upwind with a min mode limiter, and it is fully explicit. It's not in implicit mode, but it's parallelized with multi-threading on GPU platforms. And this code is now running in various organizations like ADA, ADE, DRDL, etc. And we also use this. This is a very workhorse code for us because very fast we can generate the mesh and give the results. And these are some of the developments which we did on this. And we have now included the multi-grid technique on this. The multi-grid acceleration is there, multi-core, multi-GPU version, and multi-grid CPU version. And so we have done special techniques in this, which actually enhance the improvement of even the CPU itself. Because as you know, all these CFD codes are memory bound. And so if you want to use the GPU platforms, we need to have a single instruction, multiple data type of architecture. So we need to group these cells before doing the computations. That means we have separate, the computations are done group by group. We have partial cell, then boundary air cells, partial cell whose neighbor is split, an air cell whose neighbor is split, partial cells whose neighbor is split. They're all at different categories, and so that you get maximum benefit from the GPU. And by doing this computations, the CPU performance itself has improved by something like 3x, 4x. So that is the advantage you get in the GPU. And we also have an unstructured based parallel RAM solver, which is aerospace vehicle aerothermodynamics called Pravaha, which we have very recently developed, and we have worked on for the past around 5 years. And this also we have, this is not on a Cartesian mesh, this is on a unstructured mesh. So, but the mesh generation has to be done by some mesh generation tools. And with this also we have all these various types of solvers like AUSM, AUSM plus, Rho, HLLC, resonance schemes. But what is the challenge here is actually, if you see, to build robustness in the CFD codes. That is where the real things comes. And in fact, if you are using these solvers which are open source, you may find it a difficulty in those areas. Because what happens in industrial framework, suppose you want to do a very fast computations, your mesh may not be that much, very accurate. There may be the quality of mesh may not be that good. There may be more skewness. But then your solver should be capable enough to handle those and take those things into account. You may lose accuracy. Instead of getting maybe coming to 95% accuracy, you will get 90%. But in an industrial framework, that's okay, because when we explore various configurations, we want to weed out some configurations, so even 90% accuracy is good enough. What is important is you get very fast results, and you should be able to automate and couple with optimization techniques. So that is the importance of this. That means it's very important to build robustness in the solvers. And we have done that using some special techniques. And so these are some of the applications which we have done here. And this is on a Q-escape system with all those jets. And we are also on the reusable launch vehicle technology demonstrator. And we are also having something called the Spices workshop. And, we converted during this during symposium of applied aerodynamics, which are going to be converted done in December 12th, where we put a standard problem and ask the CFD groups to solve this, and then we meet together and see how good it is, and the experiment results are not revealed. So like that, we are going to have a hypersonic air intake on December 12th. The geometry is given to all the organizations. There are something like 15 organizations going to participate, and we will see how the results are with comparing with the experiment results. Now let us see some of the applications, and this is on a typical flow field at the GSLV at Mach number 0.9. You can see a normal shock, terminating normal shock. Now these normal shocks will start oscillating and will give rise to acoustics. That is where you have problems in getting from CFD, which you need to get experiments. But you can very well get the forces and moments from this CFD techniques. In fact, it is like a fluid dynamic zoo. You have you start with laminar, it becomes turbulent, then you have attached flow, then you have separated flows, you have shock wave interaction, expansion fan, vortex flows, base flows, large scale vortex structure, flow entrainment, reverse flow, shock interactions, barrel shocks and potential core. All those things are there in this, so it's like a fluid dynamic zoo you can see in this particular flow field. And then that's what I told here. This is a terminating normal shock on the cylinder. of the GSLE this one, but the real challenge is to get back what is the acoustics on this. Now, these are some of the challenging flow problems you can see here. We have certain things which are already carried out. This is RLV reusable launch vehicle technology demonstrators, scramjet, GSLE Mark III, crew escape system at the Padabot test, and we had very recently done the landing experiment, the Chandrayaan 3, the test vehicle which we have done recently, the Gaganyaan, and then we have the future, the RLV orbiter and the scramjet. The airframe integrated scramjet with an air-breathing engine, which the thrust minus drag positive is a very, very challenging thing. It is something like an S51. And high angle of attack aerodynamics for RLE landing experiments, multi-jet interactions in Chandrayaan 3, and also the dust that is coming because of the reverse flows, the test vehicle with the crew escape system, and we have also challenges in one mission of the launch vehicle, Mark III, wherein we have the two-phase flow with the sloshing involved, and winged re-entry of orbiter of RLV orbiter. Parachute inflation aerodynamics is one of the very, very critical things. What happens during the first few seconds when the parachute is getting inflated? Are you able to do an FSI, full structure interaction, and get the loads and see whether everything is fine or not? Then inflatable aerodynamic decelerators, these are things. And on the bottom side, you can see our capability in terms of facilities. We have now going to have capability of internal capability from 0.2 Mach number all the way to Mach 12, and we also have going to have set up a 2 petaflop supercomputer very soon. And this is some of the very typical things you can see here. This was the earlier configuration of the launch vehicle Mark III, which had a straight nose cone and also the strap-on also straight. And then on the left side, we improved upon it and then made it to a standard nose cone. What I want to stress is there is on the strap-on to nose cone attachment, there will be a vortex that will be shed, and this will give rise to larger acoustic levels. So you can see this is the case with the straight nose cone, and the other one is the standard nose cone. And this was actually giving us larger acoustic levels. And this is on the cut plane. You can see there a typical the shock vortex interactions, which is enhancing the acoustics downstream. And this was what we got. We measured it actually, and we got benefit by doing this. We had almost 9 dB extra we got in the adapter just behind the strap-on nose cone. So this is the benefit you get by doing this such studies. It's an unstudy, of course, is the URAN study. And the way in which we do the aerodata methodology is, of course, we have this is the flight configuration. We have the wind tunnel test. And of course, the wind tunnel will not be same as the flight configuration. So there may be some differences. So that difference is called the geometry correction is what the CFD does the corrections. And then suppose there is a jet. So you cannot do experiments with jets. So we either do it with a cold flow experiment in jet, and a hot flow from CFD, and these things are getting accounted. That means you have a basic data from internal, you add the corrections of geometry and get from CFD and give the flight data. So this is the way in which you generate the aerodynamic data for the entire vehicle, which is used for the control studies. So this is the typical load distribution which we give. That is what is the load, it's a meter per radian, and this is what is going into the structural design. In fact, if you see, all the structural designs are initially done using CFD and then only verified by means of experiments. That means the CFD has to play a very important role right from the design phase to actually finalize what should be the structures. So this is another important aspect of the CFD. Then another thing is on the base heating of the launch vehicle. As you know, that when the launch vehicle climbs the atmosphere becomes, the pressure drops, and so the jet pressure ratio, that is the exit jet pressure to the atmosphere pressure, increases, and the jet plumes. And when you have this pluming, what happens is that supersonic flow, like you can see from Mach 2.5, there's a jet-jet interaction. And, that jet interaction causes a shock. And then what happens is there is a reverse flow that is coming here. So the oncoming flow is not able to penetrate those shock-shock interaction. So there's a reversing, which gives rise to heating in the base. And this has to be quantified, and we should define the thermal systems for this. So this is what we first quantify, what is the heat flux that is coming because of this, and then do special experiments to design those TPS. So this is the one typical applications. Then another interesting thing which I would like to tell, in one of the flights of GSLV, we had the first flight where, when all the strap-ons don't generate the sufficient thrust correctly, around something like don't generate more than 98% or so, they will cut off. So one such thing happened, and one of the strap-ons, although the cutting off has happened in all the 4 strap-ons, but only the fire happened in one of the 4 strap-ons. Then the question was, why only happened in one? Because you have a fuel-rich propellant that is coming out and mixes with the external oxidizer, oxygen-rich, and then there is a burning that is happening. So we did the simulations, And with the wind prevailing at that time, and we can see that there is a vortex found in the at that particular strap-on, and because of the buoyancy, it comes up, and that's how you see only in one the plane in one of the strap-ons. And this is another thing, just on the launch pad, which you are seeing the jet flows. And but what happened at around 2 seconds later, at 5 meters, you can see a reverse flow of jet that is coming between the umbilical tower and the launch vehicle. And this particular simulations was done. We wanted to see why this is really happening, and so we had the CFD simulations done at this particular conditions. And yes, indeed, we found out that there is a reverse flow of the L40, that is the liquid strap-on is reversing, and we want to know why this is happening. So what really happened? This is on the launch pedestal. So when there is the jet that is impinging, it flows in all directions. Now we can see here that there is a condition where you have the launch tower here. So this is not allowing it to go in this side. So if you take a cut section in this, what we are seeing is there is a fountain jet that is formed. So because of this fountain jet, we are seeing that there is a reverse flow that is happening. So how do you prevent the fountain jet? You just put those diverters there, and then we indeed did that. And then we can see here that we are not seeing any reverse flow. This was what was done, and it was done way back in the year 2000. But I just wanted to see, because this is one very important applications, where CFD is able to give solutions to this. And this is what you can see on the plant side, because the diverter, you are seeing that the jet is getting diverted. Now there is also another problem is on the L40 gimbal. See, when these nozzles are the gimbal, and that's how the control is getting activated. Now we need to find out what is the load, aerodynamic load on the nozzle, because the control system needs that input. But then when you do the internal experiments, you do without the jets. And we found out that if you do without the jets, you get very large load, and that has a problem with the control system. So when we did with jets, we could find out that the loads were indeed very less. And that's what you can see here in this graph, where experiments were done without jet, and we do the CFD. And we also do CFD without jet, and say, okay, when we have a confidence that is built up without the jet, and then you design for this with jet, and then we also got a comparison from the flight, and we really got a good comparison of the moments that is coming because of this. So this is another application which I wanted to highlight. And these are the several types of steady pressure measurement that is done on a launch vehicle, and we see at various parts. I'm just showing them typical match that is there, and these are all fairly tractable problems at different places, where on this portion, on the red portion, we can see here, and this is on the transonic Mach number, we have a sudden dip in the coefficient of pressure. Anyway, these are all well captured by CFD. There is no issue. And this is on the boat tail, where you have a separated flow, and there only we have some problems, because when when the flow is separated, you have the issues of getting the pressure very exactly, unlike the attached flows, and because it already depends on the turbulence model which you employ. This is another important thing, is on the stability of the jets. Now you can see here, this is without jets. But as you know, when the launch vehicle goes up, there is a jets are there, and that really affects the stability. Now you can see how we compute the stability for this. You do a CFD with jet off and with jet on, and what you can see here is up till the base, there is no difference. But at the base region, you can see the jet-jet interaction alters the flow field. And because of this, what really happens, it becomes really unstable, more unstable. And this is what you can see, the palettes, which shows the effects of the jet-jet interactions at the supersonic Mach numbers. And that's what we see it. And we really notice that there's a decrease of CN alpha by 14%. And XCP was moving towards the nose, that is making it more unstable. You can see the center of pressure location without jet and center of pressure location with jet. Well, this is another application which you wanted to show, was on we put a flat shroud on the base of launch vehicle Mark 3, because what we found was the jet, we thought that flat shroud, we are seeing that there's a flow that is getting separated and reattached on the nozzle. And this particular problem wanted to be alleviated, so we put a flat shroud so that it just doesn't reattach on the nozzle. And that's what you can see here without the flat shroud. And with the flat shroud, you can see very clearly how much the pressure reduces on this, and thus reducing the loads on the gimbalable nozzles. And this is all the experimental validation for that. This is another thing which I wanted to highlight. Of course, there is also unsteady problems. That is, when you start, when you start the engine, there is the nozzle will be having a closure. That closure breaks, and there is a jet that is coming out, and there is what's called the jet overpressure has to be quantified. and all these subsystems at the base has to withstand that. So this is one such unsteady simulation which we carried out to quantify what is that, and these thermal boots are designed to handle that. Well, this is on the Chandrayaan-3, which I wanted to tell, and so this is the this one, which all of this I need not have to delve in detail because it's quite popular. And these are the several types of firing which you do, and then on the Chandrayaan also, and this is the approaching this. And but what I wanted to tell was on the fluid dynamic aspects. Now you can see the jets are fired, and when you do this, there's a jet-jet interaction that is coming, and which causes a reverse flow. And we need to quantify the heat flux that is there, and all the thermal protection system has to be designed for that. And we have done computations for that. And the earlier things, when you have two jets that is firing, you have the reverse flow of the dust that is coming will get lifted up. And so this time in Chandrayaan-3, we had only single nozzle. We did not have the two nozzle, just to alleviate this particular dust problems. Well, this is on the winged re-entry vehicle, and here you can see that we have the various phases: the hypersonic phase, the terminal area energy management phase, and approach and landing phase. And this is a typical case where if you do a hypersonic chemically reacting flow, we can see the perfect gas and the real gas. The real gas is showing the very less shock standoff distance. That is mainly because when you have a very high temperature at the stagnation point, when the oxygen start dissociating at 2000 Kelvin, nitrogen started dissociating at 4000 Kelvin. And when the dissociated gas, they will become cooler. When you have cool gas, you can push more mass in the same stream tube, then that's how the shock gets closer. So these are all the phenomena that is there. And we had also done various simulations to quantify these heating levels. Of course, the wall also plays an important role. We have something called the catalytic wall and non-catalytic wall, which means that the dissociated species called the O, the nascent oxygen, and N, they can recombine at the wall and dump the heat of diffusion and the heat of that is the joining, that is the dissociation heating will get dumped up on the wall, and so that has to be prevented. And so we have special materials like RCG, which will prevent this recombination of the species, recombination of O to O2 and recombination of N to N2. And these are some of the things. And there's also something called the gap flow, because these elements has to be moved and there will be a gap. And when you have this gap in hypersonic flow, what is the gap heating? This has to be quantified correctly, and we have to design the seals for this. And these are all some of the RCS that is fired. And in the hypersonic flow, how the RCS affects the aerodynamics of this also has to be quantified. And these were all done using CFD. And this is on the very landing experiment which we did. And, that is the approach and landing phase. And that portion has been done now. And autonomous landing has been enabled. And for this also, we need to generate the aerodynamic coefficients for the control design. And here also this was done. And this is with the helicopter downwash. We had done first initially in the MI 17. And now we have done later on with Chinook, and this is the downwash of that, and seeing that the downwash doesn't affect the helicopter, and all these CFD computations were done to quantify this. And this is at various angles of attack when it is coming down, and what should be the limiting angle of attack and what the stall angle of attack. All those things we had computed. Of course, we also done several internal experiments in IIT Kanpur and NL. And so we had seen that this is how the wing vortex and the vortex breakdown happening at what angle of attack. So these things were quantified using CFD. Now coming to one of the very interesting problem is the moving unsteady problems. See, we do a heat shield separation. Now normally what we do is, now when we should be able to minimize the cost which we are doing by doing this testing. Now, this heat shield separation occurs almost at rarefied conditions near vacuum. Now, as you know that none of the launch vehicles we do without testing. So the philosophy is test as you fly and fly as you test. So if you want to test as you fly, then you have to have a huge vacuum chamber to accommodate this heat shield, and then we have to separate on that, which costs a lot of money. And so what we have done is, why not do in the ground and quantify what is the effect of the atmospheric this one, and then see what will happen for the flight. So that's what was done for this particular condition. So we did this heat shield separation on the ground, and on the ground what happens is, so this is a moving body problem which we have done using a Cartesian mesh. So this is of course I did not go into details of this. So we have to have a special type of Riemann problem to do this, and some cell merging and moving boundary techniques are there. But what I want to tell in summary is, this is the heat shield that is getting separated, and so initially you have a very large acceleration. So we have the velocity that is given as an input, And with this velocity as a moving boundary as an input, when we compute, what you can see here is how at 8 milliseconds, 14 milliseconds, you can see a pressure drop. And this pressure drop and what is measured is exactly matching. And because of this pressure drop, there will be a collision, and you will find that there is a collision, but this will not happen in vacuum. So that's what we found out. And so we are now doing away with all this thing, because but Ariane does with the rarefied conditions which cost a huge money. So this was debated in way back in those years, and then we avoided this by quantifying from CFD. This is another typical things on the inflatable aerodynamic simulator. This is coming down. We want to recover some objects by this aerodynamic simulator. The flow is from right to left, and you can see very high angles of attack, high Mach numbers, complex flow, shock interactions, high aero heating, and all those things which we are done. And we are seeing the matches with the commercial code Fluent and our own code Pravaha. And so normally what we do is we have commercial codes also, mainly because there are many conditions where you cannot do experiments. In such cases, you should have minimum code to code, at least 2-3 codes should have almost the same result. So that is the way which we go ahead with our design process. And this is the sensitivity of turbulence model on the heat flux. So this is on the scramjet vehicle, which we wanted to demonstrate. And so this particular thing, and this experiment was planned for 5 seconds. So we have a design emission with this pillbox. In fact, this is a low-cost mission using sounding rockets. So this is what was done. And okay, this is got mixed up. So for this, we need to do the chemically reacting flows. And so this is one of the Leher cylinder case where you have a stoichiometric mixture of hydrogen and oxygen at Mach number 3.55. What is interesting to note is, although there is a temperature rise that is happening because of the shock wave, but the combustion happens only downstream, which means that there's a finite time for the combustion to occur. So this is a typical case of validation of a non-equilibrium chemically reacting flow. A Leher cylinder of 15 mm dia is a typical case for non-reacting flows. And we can see this is the shock front and the combustion front later. So that is the thing. And so that is the validation which was done. And this is the trajectory in which, we had gone and we had done some experiment. And you can see here there's a non-reacting flow and the reacting flow. What is important is to demonstrate supersonic combustion. And what do you mean by supersonic combustion? When the combustion occurs, there should not be any upstream influence. And that's what we are precisely seeing from this plot. That is upstream of the strut, whether it is non-reacting or reacting, it is exactly the same. And we had done measurements across between the two struts. And to verify this is what the next plot shows. You can see the blue one is actually the blue graph is the data which we got from the flight. That is the flight measurement non-reacting is the green one, and the flight measurement reacting is the black one. You can see here up to the strut end, there is no difference between the non-reacting and reacting. And this clearly demonstrated that we had achieved supersonic combustion. And then we also had further points at different conditions. And we could even get the flame out of this. So this was a very highly successful experiment of the scramjet demonstration. As you know, the scramjet is always called lighting a lamp in a hurricane. So that is how it is. So you stabilize the flows behind the strut and then do the combustion. But there are some problems even in this, in air intakes. You can see here that suppose we are now working on a airframe integrated scramjet engine where we have 3 ramps, and the cowl shock that is impinging on the ramp causes the separation bubble. And this separation bubble is very dangerous because what happens is the separation bubble grows. There will be an unstart of this engine, of this intake. So we have to very correctly able to predict the size of the separation bubble. And we did have surprises because there will be a lot of differences if you employ a real reversible K-epsilon model and SSTK omega model. Precisely getting the size of the separation bubble is very, very difficult unless you tune the coefficients of those turbulence models. So these are some of the things. Of course, we are doing away with that by retracting the cowl tip or making the shock strength lesser. These are some of the things which you are doing later. This is on the end-to-end mission of the TVD1, and where we had phases, and we had we wanted to demonstrate an abort of the crew module. This was done very recently in last October, and this is on typical flow field on this. And we also do internal experiments, oil flow visualization, and the CFD, and how with the HEM jet, that is the high altitude escape motor jets firing, and how it's getting separated from the crew module. All those simulations are being done. And this is on the Gaganyaan mission profile, and this is where we have the orbit of 170 with 40.8. This is a very challenging mission where it's going to happen very soon. And for this, all the preparations are on. But here, what is important is the re-entry phase, where you have a very high heating coming, and we should have a proper thermal protection system, and also the deployment of parachute and the associated oscillations and things like that, and the dynamic stability of this. And here we have done the simulations for the Mach number 21 and alpha minus 16, because that is the trim alpha for this. And we had done the blackboard studies with saying electron number density variation, and this is a typical numerical simulant, and we got very good match with the test data, almost 4% match with test data. And this is my final slide, and this is the space vision for 2047. We are going to have a Bharatiya Antariksha Station by 2035. The first module will be by 2028. The lunar sample return by 2030, and of course we are also planning a soft landing on Mars. Indian moon landing by 2040, and we are also having a Venus mission. So many of these things are approved by the central government, and we are working on this. We have a lot of exciting missions. There's a lunar sample return also is there, and a lot of work for the CFD and the associated technologies. So I find that there is a lot of exciting opportunities for working in this space vision for 2047. In fact, there are a lot of people involved. It is not only just the ISRO. There is a lot of academic institute, the private industries. They're all hand in glove in achieving this. So thank you very much for your patient hearing. And if you have any questions, I can take.
Thank you, Dr. Ashok. So we do have a question from Professor Bose.
Thank you, Dr. Ashok. And I think the first thing I would like to really express our gratitude and thank for accepting to speak and give us a lot of information how CFD is being used in the national projects. So I have one question, like you mentioned that you are also inclined using this open source tools such as OpenFOAM for your problem, and you have developed your in-house codes, which is fascinating to see, and you also use commercial softwares. So can you briefly share your thoughts on this? So, and do you see?
I tell you. That's why I told the open source software.
These open source tools in these projects.
Yeah. See, for example, actually the DSMC foam, that is a very I will tell you very effectively applied in DSSC. That is mainly because none of the commercial codes have the DSMC capability. Mainly that doesn't drive business for them. That's why, and the DSMC is never a design driver. If you take a launch vehicle, the design driver is basically transonic Mach number. So where it is a compressible viscous force. That is why if you see almost 80 to 90% of our computations is on compressible viscous flows. That is why all our things are basically density based solvers. In fact, if you see Fluent, their strength is on the low speed flows. Our low speed flow applications are very less. So that is one thing. But then what we found that there are some areas where we really need to do it. For example, suppose I want to know how much time a satellite will be there in the atmosphere, in a rarefied atmosphere. I need to get the drag of that. So if I want to find out the lifetime, the drag is a very important aspect. There I need to have this capability. So we had used that, and very successfully I can say that the DSMC foam was used. The only issue is then what we wanted was, we wanted to couple, for example, if you take the Chandrayaan 3, there we had seen that you have continuum flow for some time, then you have transition, and then only you have free molecular flows. We wanted to bridge the continuum flow to the DSMC. So that is what we, if you have open source, you can do all those things as well. It will be possible to do that. So that is our take on the DSMC foam. But on the supersonic flow, we had used SU2. I don't know, because this is more, you are more onto this. SU2 also is another good code at Stanford University. But then what we found is for some of the complex problems, like if you start doing at very high jet pressure ratios with jets, the solutions normally blow out because you have negative energy coming into the solutions. And if you don't properly tackle by doing appropriate CFL number and also the grids, you will have problems. You may have to drive the solution. So that is where the robustness of the solver becomes important. And most of the time in industrial setup, we require solutions in 1 or 2 days, because the vehicle will be on the launch pad and they will ask questions just 2 days before, and we have to give answers. robustness is very important. So we cannot, so that is one thing which we found, that the commercial solvers, the open source solvers need to improve on the robustness. So this is my intake. I don't know whether I have answered your
Sure.
question or not.
Thank you, Dr. Ashok. We are looking forward to interact with you more from the FOSSEE team.
Yeah, I have a few questions. Thanks. Yeah, this is Kannan Moudgalya speaking. We are really happy that you could address this gathering. Sorry, there was some delay in getting in touch with you because we had to go through some proper channels and things like that.
Yeah. I superannuated last month. Yeah.
That is also the reason why we could not invite you to join the advisory board. We would very much like you to be a part of our advisory group and guiding us how we should spread this activity. In particular, how such an activity can be helpful to ISRO, for example. That will be a fantastic thing. That can happen in many different ways. For example, suggesting some problems that students or faculty members across the country, or even the startups. We have design consultants with us. Some of them may be interested in addressing some of these problems, number one. Some of them may be interested in developing new algorithms, robust algorithms, for example. And the third one could be integrating some of the things that you have developed, helping integrate so that, because as Dr. Chandan Bose is part of the governance, open form global governance group, so he knows all the people. So in case ISRO develops something and you want to integrate in a particular way so that it is reusable for you as a part of your version of open form, things like that. I think we can think of many different ways where we can contribute to the amazing work that ISRO is doing and FOSSEE is doing. So for all these purposes, it will be great to have you on our advisory group.
Yeah, thank you very much. I will say there are some niche problems. See, for example, the spray that is coming out. See, for example, when you have a kerosene injection, we do a barbitaging, that is effervescence. Now, how these sprays are coming and what type of, there are something different types of flows there. These are all very difficult to track, even commercial solvers don't have. But with open foam, I think it should be possible. So we can work on niche problems like that. Unsteady combustion is one niche area. How to couple the slosh and the two-phase flow with combustion, that is another important area. Acoustics is definitely a very, very interesting area. Very much the commercial solvers don't have capability. Like LES and this, if you are able to do that and get acoustic like jet noise and all with reflections and things like that, it'll be great. So these are, I am finding that there are a lot of scope if you work on niche areas.
Okay, thank you, Dr. Ashok. We will get in touch with you later. Thank you.
So first of all, very good afternoon to you and one and all present over here. So my question was, like you said, you are doing some rarefied gas dynamic studies with the simulation, and 1 and 2 days you need results. So if rarefaction is very high, like Knudsen number goes beyond 1, or for example, consider 0.1 also. So where this Knudsen number is 0.1 or in that range, that time it is computational power is very limited to give the results in 1 and 2 days.
Yeah, that's true. So what I told was the only 1 or 2 days is not on the DSMC type of flows. As I told you, the DSMC type of flows is not a design driver. It is basically, I told you that because at that conditions, the heat flux is low, the aerodynamic forces are low. So it is never a design factor for any of our structures. But then it becomes important if you want to know the lifetime of a satellite, because the lifetime of a satellite will depend on the drag that is appearing on it. So you should be able to correctly predict the drag. For that only, I told that was is important. And then some of the conditions like what I told was on the jet-jet interaction at a very rarefied conditions, there it is important. But then what we always do is, as an engineering thing, if you err on the conservative side, so we assume it to be continuum and then push it, like suppose the external pressure is say vacuum, we'll consider 0.1 Pascal and do the computations and get away with that. So that is the way it is done. So as you said, yes, but it will be interesting to do a lower Knudsen number. It will be very challenging because your mesh size will go like anything, billions of cells, because as you know, it should be less than the mean free path. So that is the issue there. So we normally don't do at 0.1 Knudsen number. We do much higher than that only.
Okay, so yeah, so we can help you in that sense. So was my
Yeah.
that's why I asked this. Thank you, sir.
Thank you.
Thank you so much, Dr. Ashok.